Hello everyone, welcome to the Spectral Theory in the Cloud seminar. So today it's a pleasure to have David Tewodrose. He will talk about critical metric of eigenvalue functionals via subdifferentials. So David, we keep an eye on the chat if there is any question, but feel free if you have any question to unmute yourself. So David, the floor is yours.
Okay, thank you very much, Asma, for the introduction, and thanks for the invitation. It's a pleasure for me to speak to this seminar. So I will talk about the joint work with Romain Petrides from Universit Paris Cit. So let me start by giving you the setting of the work. So for my whole talk, M will denote a compact, connected, smooth manifold of dimension n is 2. Rm will be the space of C2 Riemannian metrics. So yeah, Riemannian metrics and C2 because it's more convenient for me. And I will consider some spectrum lambda k that depends on a Riemannian metric G. So it's a discrete spectrum of some operator AG. So we give examples in a minute, but classical examples are the Laplace-Beltrami operator and the Dirichlet to Neumann operator. And so this spectrum is, as usual, sorted in non-decreasing order. And now, what we do, we take a certain number of elements in this spectrum. So this number is big N, and we consider a Lipschitz function f from R big N to R, and we define a functional that takes in input the metric G, and gives as an output combination of some suitably rescaled version lambda k bar of the eigenvalues lambda k, and so a combination of the nth first elements of this rescale spectrum. So this is a general, let's say, framework of my talk. I will not. So concerning the scaling depends on the situation. I will not spend too much words on this, but just keep in mind that we make some combinations of suitably rescaled eigenvalues. And the main question, so where is the question? It is here. The main question is, what are the properties of the Riemannian matrix G that are critical for this combination of eigenvalues, of rescaled eigenvalues. And so it turns out that, and most of you probably know that critical metrics in classical contexts are related to eigenmaps. So what I call eigenmap here is the following. It's a map from the manifold to some Euclidean space of dimension big J, and such that, so it is called an AG eigenmap. So remember, AG is my operator, the operator I consider the manifold. If the coordinates of the map phi are eigenfunctions of AG, and each eigenfunction corresponding to the eigenvalue, they're sorted in increasing order, and the coordinates are also sorted according to this order. And we also said that the map is the eigenmap is L2 orthogonal if the coordinates are orthogonal with respect to the L2 scalar product. Okay, so this is, for now, this is just a let's say formal definition. And so now I'd like to give you some examples of spectrum that we are interested in with Romain. So the first one is the Laplace spectrum. So for this Laplace spectrum, we assume that the manifold has an empty boundary. So the Laplace spectrum is the spectrum of the positive Laplace spectrum. So you take the convention of the positive operator. So the eigenvalues form a discrete sequence of positive numbers. Okay, so that's classical. And so I mentioned it. Another spectrum one can be interested in the Steklov one. So for the Steklov one is defined for manifolds with a non-empty boundary. And so this spectrum is the spectrum of the Dirichlet-to-Neumann boundary operator. So dj, which is defined as follows. If you have a function u that is defined on the boundary of your manifold, then you extend the function u harmonically on the wall manifold. So u hat is a harmonic extension on the wall manifold of u. And then you take the normal derivative of u at the boundary, and this defines the Dirichlet-to-Neumann operator. And you can show that this operator emits a discrete spectrum, which is made of positive numbers, converging to post infinity. Okay, so this yes, most of you know this context, and there are three other spectrums that I'd like to mention here. So the first one is so in the case of closed manifold and dimension n at lib3, the conformal Laplacian is a perturbation of the Laplace of the Tommy operator, perturbation by some constant Cn, which has some 1 by n minus 2 in its definition. So that's why defined for manifolds of dimension at least 3. And Rg here is the scalar curvature of the Riemannian metric G. And so this operator, this conformal Laplacian, also has also emits a discrete set of eigenvalues. And contrary to the two previous cases, these eigenvalues may be negative. And so the two last examples are the Panites spectrum. So Panites spectrum is obtained from the Panites operator, which is a perturbation of the B Laplacian, perturbation by lower order terms, lower order terms, and in this case, the spectrum may also emit negative values. And lastly, the Panites and the conformal Laplace spectrum are particular instances of the GJMS operators, which are defined, so which are operators with some parameter m, which gives the order of the operator. The operator is basically mth power of the Laplace-Beltrami operator plus lower order terms. And it's also an elliptic operator. So we have also the same kind of spectrum. And so we are interested in all this, studying all these spectra at the same time. Yes.
So for the last two ones, so you put boundary non-empty. So which boundary condition?
Because it's a mistake. It should be. I wanted. Yes, sorry. It's not a boundary operator. These are not boundary operators. Thank you very much.
Okay, thanks.
Okay. Any other questions so far? I haven't checked the chat. No. Okay. All right. So one major trouble when studying this criticality of combinations of eigenvalues, actually studying criticality of even one single eigenvalue seen as a functional on the set of Riemannian metrics, is multiplicity. So it's well known. So I've made a naive picture here. You perturb some metric G in some direction H, so G plus TH, and at the metric G, the first eigenvalue has multiplicity 3. And as soon as you go away from G, you have 3 distinct elements. And because of this, you have some non-smooth phenomenon that appears here. And here you have some break in the regularity of the branch. So the first question is then how to define criticality if you don't have notion, if you don't have smooth functionals. Then one possibility, the classical one, say, is has been given by Nadirashvili in 1996. In the case of a single rescaled eigenvalue, so the function is just one Laplace eigenvalue, actually, in the case of Nadirashvili. G is critical if anytime we perturb G in a smooth way, so GT, then as t goes to 0, we either have f of gt that is higher than f of g plus some small o of t, or the opposite. So when we approach from one direction, we are infinitesimally above f of g or below f of g. And this definition allows to get many results. So I'm going to give some of them. I've tried to list them. I hope it's no. I haven't made mistakes in the reference. Otherwise, I apologize. So the first. Okay, so if J is a critical for one single Laplace eigenvalue, so then there exists a delta G eigenmap from M to the sphere Sm-1, where M here is multiplicity of the eigenvalue at G. And this eigenmap is a conformal minimal immersion. In the case of Steklov eigenvalue, this was studied by Fraser and Shane in case n equal to 2, and then Kapuskin meta in the case greater than 2. Then instead of having a delta G eigenmap, we have a dg eigenmap. So to be more precise, dg eigenmap from M to field Euclidean ball actually is the dg operator, if you see it as a boundary operator, so an operator defined on functions on the boundary, then the maps will be map M to the boundary of the ball, and then you use the harmonic extension of these coordinates to get the map from M to the ball. And in this case, you get free boundary conformal minimal immersion. So this is a by now well-known result, and what is known also is that you have a converse statement that from minimal immersion from M to Euclidean sphere, you can get a critical pullback metric for some rescaled single eigenvalue. And now there's also a version of these results in the case where we restrict the scope. I mean, we restrict the domain of we restrict our functional to a conformal class. So here, by conformally, I mean restrict to the conformal class of G. And then in this case, what we obtain is so in the case n equal to 2, we obtain harmonic maps. In the case n higher than 2, we obtain n harmonic maps. So for this n non-degenerate harmonic maps. And here also we have a version for Steklov and a version so a version for Steklov, yes, and a converse statement. And now, so I'd like to give you another result, which is due to Romain, and which really deals with combinations of eigenvalues. So not just one single eigenvalue, but combinations of eigenvalues. And so Romain treated the case of Laplace and Steklov on surfaces in two different papers published recently. And so he made the assumption that the partial derivatives of the defining function f sharp evaluated at the Riesке spectrum of the metric we're interested in. So these partial derivatives that I call dkg, are positive. And so under this assumption, he showed that if a metric G is critical for F, so F and so with Laplace spectrum, then you get again an eigenmap, conformal, minimal, immersion, but this time instead of having as a the codomain of your eigenmap is not a sphere anymore, but an ellipsoid. And this ellipsoid is defined as follows. So you see here the equation that defines the ellipsoid. And so these mu i's here, mu i's, are the distinct elements in the spectrum. Okay, the Aleph I here is the batch of indices that correspond to a given mu I. And so the ellipsoid then is defined as you see here. So you have directions that correspond to each index, and these directions are weighted according to the corresponding eigenvalue. And since you consider combinations of eigenvalues, the weight is different. And so in the end, what you get is an ellipsoid. In the case of a sphere, if you consider only one given eigenvalue, then you get only one weight, one possible weight, and so your ellipsoid reduces to a sphere. Okay. And here again, so in the case of the Steklov spectrum, this time the target is a filled ellipsoid, so let's say inside the ellipsoid, and just like in the previous cases, you obtain a free boundary immersion, free boundary map. Okay. And so yeah, I think I've introduced other notations here, and going on, I'd like to comment a bit on them. So here we have a sum that goes from 1 to I and j. So I and j is just the index I. So lambda n, so the last eigenvalue in the piece of the spectrum we are interested in is equal to mu I. Okay. And the other notation that I will use so later is this J and G, and J and G is simply the maximal index, such that here there's the same typo, lambda J of G is equal to lambda N of G. So I made a picture here, maybe to make things clearer. So here, let's say you have the mu i's, mu2, mu3. So mu I here in picture equal to lambda1, lambda2, lambda3. So this set of indices is Aleph1. This set of indices is Aleph2. And so for instance, if n is equal to 6, then Gn is equal to 7 and In is equal to 2. Okay. Okay, now, so in this statement by Romain, there is this assumption that the combination has positive partial derivatives, and we'd like to remove this assumption. So that's one question, and another question that motivated our work is how to also deal with all the spectra. It's all these spectra, they are treated with similar tools, so there's maybe some way to treat them all at once. And so that's what we tried to do. And for this, we proposed a notion of criticality that's a bit different from the one considered in the previous papers, and which is the following. So we say that a metric G is critical if 0 belongs to this guy here. And this guy, what it is, it's the union of the sub and super differentials of f at G in the sense of Clarke. So I'm going to give the definition of this sub and super differentials of f at G in a moment. But I just want to point out that this notion of criticality is interesting because it's so not if a metric is critical in the sense of Nadirashvili, it is critical in this sense. Okay, but so there are several advantages of this definition, and one advantage is really to treat any kind of combinations, any kind of combination of eigenvalues, while the one by Nadirashvili is more, so it's kind of made for one given eigenvalue, and it works for very rather particular combinations like combinations with whose partial derivatives are all of the same sign. And so with this definition, we obtain some results. So I'd like to present two of them. So the first one is the following. So if metric J is critical, so critical this time in the sense of the previous definition, critical for F with Laplace spectrum, then there exists an eigenmap, so a Laplace eigenmap, which is L2 orthogonal, and which maps M with a metric G to some object. And this object is Q epsilon equipped with H epsilon. So here epsilon is an uphold of signs. Okay, so +1, -1, or 0. And so I will not give the exact meaning of this, but these signs are, I mean, these numbers, sorry, are related to the signs of the partial derivatives of the combination big F. Okay. And now, so from these signs, we can define a quadratic form H epsilon, which is just given like that. So you take for given vector C, you take the sum of the epsilon k C k squared. So it's possibly non-definite quadratic form, may not be positive definite or negative definite. And then out of this quadratic form H epsilon, we define a quadric in the Euclidean space R J and G as follows. So if you remember the case of the ellipsoid in the statement by Romain, there were no epsilon square, epsilon k, but here we just add these signs in front of the coordinates ck. So we have this can be written in another way. Can be written as H epsilon of big lambda c where big lambda is the upper given by lambda 1 g so on until lambda n g. Okay, and some of these lambdas are all equal one to the other, they're all equals to the to some mu I, and so that's why we will obtain this this form of the expression H epsilon lambda xc. Okay, and so this extends the result, the previous result by Romain in the Laplace case. So we have also a version in the Steklov case, but I decided not to include it here to keep things reasonable for today. And so we also obtain a converse statement. We also obtain converse statements that says that if we're given a conformal minimal immersion phi from mg to some quadric, and here, so the quadric is defined here. Okay, and just for some parameters, so some epsilon and big lambda. And if this function, so there is an extra condition to make sure that this conformal minimal immersion provides a critical pullback metric. So we need to make sure that the conformal factor that we would obtain from the direct direction, say, that the conformal factor is positive. Otherwise, we may not get a real. We may not get a pullback Riemannian metric. We may obtain some strange object that would not be positive definite everywhere. And so this is a condition. We must make sure that this function is positive. In this case, the critical metric is given as a pullback of the quadratic form H epsilon times F. Okay, so that's.
Can I ask a question about this one?
Sure.
So for in the converse statement,
yes,
is the F fixed or not?
So the F is
not the small F, big F, the function.
That's a good question. No, so there exists some F. There exists of F, but so your question is, do you mean that you can have different F or?
But basically, where is big F in here? That is big F recovered from Q epsilon?
Yes, it's recovered from Q epsilon. It's
but they could be different. Is it uniquely recovered? I don't. It's. Oh, there's like a range of f's for which.
So it's uniquely recovered up to I mean, two functions that have same first order derivatives will do the job, and so no, okay, no, so no, there is no uniqueness actually. So what we construct, so in the paper we construct an example of function that for which this metric would be critical, but there may be others. There's a choice that depends on the signs epsilon k and on some weights that are actually related to that we need to recover the exact values of the first order derivatives of the function f.
But there's basically a constructive way to provide all possible functions. There's like set of conditions that say that if it satisfies this condition.
Yes.
Okay.
Yes, I think so. Yes.
Okay, thank you.
Okay. Are there any other questions on this theorem? No. Okay. So the second theorem I'd like to give is about the conformal critical metrics for the GJMS operators. So we choose some index M. We consider the spectrum of the GJMS operator of order M. We assume that we are given some metric that is conformal to some reference metric G naught. And we assume that this metric is critical for the restriction of F to the conformal class G naught. And then, so the statement is that there exists JGM eigenmap with two orthogonal coordinates again that maps M to the Euclidean space of corresponding dimension, and such that up to rescaling this eigenmap, the eigenmap phi is here, we multiply it by this factor that depends on the conformal factor beta, and in this way we obtain a new map psi, and this psi is JGM harmonic in the sense that it is critical for this new energy. So and the map psi sends mg into some quadric. Okay, so just same kind of quadric as before. So for some epsilon that relates to the first order partial derivatives of the f sharp, we have this quadratic q epsilon, and with this quadratic form with the quadratic form h epsilon, and out of h epsilon we can define an energy, and on the set of mappings from mj to the Euclidean space, and so we say that a mapping is critical for this energy. I mean, we say that a mapping that is critical for this energy, we call it JGM harmonic. A mapping subject to the constraint of ending in the quadrant q epsilon. So this is a version of a GJMS version of the previous statement on Laplace that gave harmonic maps, or n harmonic maps. And so what's quite interesting is this scaling factor. And especially, I don't know if I wrote it. No, maybe not. So here you see that this 2m minus n well, it is such, I mean, if there is no scaling factor, right here, no scaling if 2m is equal to n. And this is the case, for instance, for the finite operator. So where n is equal to 4, and the order, so the Panis, I mean, the principal symbol of the Panis operator is the B Laplacian, so m is equal to 2, and so we have so 2m is equal to n in this case, so no scaling, and we obtain then, in the case of Panis, we obtain a Panis harmonic map from Mg to a quadratic. And interestingly, in the case of the conformal Laplace, which is also a particular instance of GJMS operator. So conformal Laplace said that n is equal to 3, and in the case of conformal Laplace, it's a perturbation of the Laplace-Beltrami operator. So m is equal to 1, so we can never have 2m equal to n. Okay. So in the case of the conformal Laplace operator, we always have this kind of scaling. Okay. And so again, we have also a converse statement also in this case. So if for some epsilon parameters, epsilon and lambda, we're given a map psi from M to some suitable quadratic Q epsilon lambda, that is JGM harmonic, and such that some other conformal factors, or I mean, it would be give eventually the conformal factor to recover a critical metric in the conformal class of G. And so if this function is positive, then the conformal metric given by multiplying G by beta to the power 1 by m is critical again for some functional. So it's the same kind of statement. Are there questions on this second statement?
I think it should also be true for slightly more general conformally covariant operators, right? I mean, not just for GG.
Yeah, it is. It is actually so what we do in the paper. So we prove a general statement for conformally covariant operators, and we deduced this this statement from this general one. Yes. Yes.
I guess the half integer case could be a little bit interesting. It's in the odd dimensions.
Anyway. Could you say it again? Sorry.
Yeah, no, that doesn't matter. I just wanted to. There are probably a bunch of results a little bit like that for critical metrics on graphs, where you allow weights on edges, and so that it's much easier, but maybe it could be a funny exercise, because we wrote a long time ago. We wrote a related paper for critical metrics on graphs with Riven, like back in early 2000s. So it's,
okay.
Yeah, I can send you some references.
Okay, I'll be happy with that. Yeah. Okay.
Thank you.
Thank you very much. Okay. So now I'd like to explain a bit how we obtain these results. So we work in a framework that we want to be as general as possible. And so here are the characters, let's say, in this framework. And the first one is some Banach space X that you can, so you can think of this big Banach space as, for instance, a space of 2-0 tensors on M, symmetric 2-0 tensors on M, and with infinite number of tensors, and then inside this big, let's say, big Banach space, we consider an open subset omega, and here you can think of this space as a space of Riemannian metrics. Okay. Then the space Y, we also introduce some space Y, which is an infinite dimensional vector space. And so one has to think of it as a space of functions, of L2 functions. And on this space of L2 functions, we define a positive definite quadratic form, which we call Q, and that plays the role of the L2 norm. So it would be the L2 norm squared, actually Q. And then so we also need a densely defined quadratic form on Y. So this densely defined quadratic form, densely with respect to Q1/2. So with respect to the L2 norm, and so this would correspond to the Sobolev. Say if we're working the case of Laplace spectrum, it's the squared Sobolev norm. And so this Q and G so are actually X dependent, okay, where X belongs to omega. So for every X, Qx, I should write it like that, Qx dot is our quadratic form. And it's if you keep the analogy with the Laplace case, X will be where the X will be a Riemannian metric, then the norm also depends on the Riemannian metric that we consider. And in the same way, G is also X dependent. And we assume that the G is greater than some minus lambda Q. So okay, so this is one of other assumptions that make sure that we can define a U for any X in omega and any U in Y in this way by taking some G. So we will call it G with thinking of gradients. Gradient may think of the H1 norm and the Q because it's a quadratic form. And then so we have other assumptions. So one important assumption is that the Vrije derivatives with respect to X, with respect to the X variable, exist for this G and Q quadratic forms. So since R is a quotient of the two, also the Vrije derivative of R exists, and has some formula and satisfies some quotient formula. And so we want R to admit eigenvalues defined by min-max. Okay, so that's classical min-max way to define eigenvalue that we have in all the concrete spectra that I mentioned at the beginning. and other technicalities that I don't want to mention now, but if you want to ask me questions in the end on them, feel free. And so we rescale this abstract eigenvalues lambda k by some scaling function, and the only the scaling function s, and the only assumption that we make on this scaling function is that it's freshly differentiable. So here, unlike let's say classical settings where people were more interested in maximization of minimization or minimization of eigenvalues, we are interested in just critical metrics. And for critical metrics, I mean, the only assumption that we need is this. Maybe for minimization, maximization, we may need more. We need something on this scaling, but yeah. And then, so we can define again from our f sharp, we can define some functional f on omega. And so it turns out that under the assumption that we consider, this f is locally Lipschitz. And because f is locally Lipschitz, then we can use machinery that has been developed by Clarke in the 70s. So here I'm finally going to give the definition of this sub and super differential in the sense of Clarke. So the first, so if we have, we're given a function, locally Lipschitz function on omega, small f, then the generalized directional derivative is defined as follows. So we have two objects, two derivatives, one with a plus that is defined with a lim sup here, and one with a minus that is defined with a lim inf. And in both cases, we consider this particular difference quotients where we not only let t vary, so it's generalized directional derivative at a given point x in some direction h, and we not only I mean the point here is that we also let x vary, where we take a lim inf and lim sup over y converging to x, in addition to having t converging to 0. And then, so what's particularly interesting with this object is that they're always well-defined. So they can be infinite, but they're always well-defined. And out of these generalized directional derivatives, we can define these sub and super differentials. So the subdifferential is a minus. Subdifferential, so it's subdifferential is a subset of the dual of the Banach space X. And it is made of linear forms, which are always under the upper generalized directional derivative in the direction of h. And in a similar way, we can define the super differential with reversed inequality. So the linear forms which evaluated in each direction are always above the lower generalized directional derivative. So maybe just to compare with the classical notion of directional derivatives, so where y does not, where x does not move, and where the limit is no lim sup or lim inf. But the problem is that this may not converge. And but well, still, when it converges, one can define a classical sub and super differential by just just working with this right directional derivative and define sets in the spaces in the sets in an analogous way. And so the fact that this directional derivative may not converge implies that, well, the classical subdifferential may be empty, while the Clarke subdifferential, actually, one can show that it is never empty. So this is one interest, one reason got interested in this in these notions. And another reason is that actually, if we have some spectral gap, so if we consider a lambda k that is greater than the lambda k minus 1 or lower than the lambda k plus 1, then actually the classical sub and super differential are not empty, and they coincide with the Clarke sub and super differentials. That's quite interesting to study the case of spectral gaps. Okay, and so the main proposition that allow us to work in all the concrete settings is the following. So remember, our definition of criticality is the one that we propose is this one, that 0 belongs to the union of the sub and super differentials at point x. And actually, this sub and super differential, one can show that they are both a subset of this set of elements that are, well, Vrije derivatives of the Rayleigh quotient, Vrije derivative of the scaling, and this come from some product rule. And so what are they? There are some, so this Vrije derivative is evaluated at some elements UK of an orthonormal family for the kind of L2 scalar product. So eventually these UIs will provide us with, and yes, maybe it's not only orthonormal, these are also, this UK actually, they are eigenfunctions. So they realize the min-max associated with lambda k. So the eigenmap that we get in the end comes from these UIs, and then we have these terms d tilde k that weight our values here, and these d tilde k's are kind of convex combinations of the first order partial derivatives of f. So they are related with these partial derivatives in a convex way. And so maybe I can jump directly here to say that now, if from this proposition 0 belongs to the, so I shouldn't have put some, yes, it's just one implication, the converse is a bit more involved. So 0 belongs to this union of sub and super differential. If we know this, then we get for free an Euler-Lagrange equation, because so we have one element in this set that must be 0. One element of this set is then given by an orthonormal family and these strange weights. So we have an Euler-Lagrange equation, and we just need to compute then the Vrije derivative of our Rayleigh quotient and the Vrije derivative of the scaling to obtain something concrete in each case of study, and out of which we can deduce geometric properties that we are interested in. Okay, I have 2 minutes left, right?
Yes.
So, yes, okay. So in the last 2 minutes, I will just explain a bit how we get this proposition. So F is a combination. So the first thing that we use is a chain rule for a sub and super differential that is that was obtained by Clarke. And so I only wrote this chain rule for under the assumption that the partial derivatives of f are non-negative. Otherwise, it becomes more nasty because you have it becomes nasty. And but somehow it reduces the study of this guy to the inclusion properties of this guy to the inclusion properties of the single eigenvalues, or the sub and super differentials of the single eigenvalues. Then there is a product rule by Clarke that says that this the sub and super differential of this rescaling eigenvalue writes like that. So here we get the sub and super differential of lambda k. And now we need to understand what's this guy. And to do this, we make some explicit computation of the generalized directional derivative of the lambda k's. And with this explicit computation and the classical Ann-Banach argument, we obtain that these sub and super differentials are a subset of some of this convex hull. And I think I forgot an x here. It's a Fresher derivative. And then we like to get rid of this convex hull, and we use some lemma from linear algebra that somehow hide the convex hull into the coefficients dks, and that's how we obtain this dk tilde.
Does anyone have questions or comments?
No, I just had a simple remark that probably some one can look at some reasonable boundary conditions, right? And for this conformity covariance.
That's what actually. So we in the paper we considered the case of a combination that that involves Dirichlet